now that we've updated our thinking about gravitational potential energy and how we can calculate it for objects that are really, really high above the surface of Earth or some other object, it's time to look at what implications that has for other forms of energy, and especially situations where we're looking at multiple types of energy together, like in the case of the law of conservation of energy. So I'm going to start right away by jumping into an example. How much work is required to move a 4,500 kilogram object from a radius of this to a radius of that above Earth? So just give me a moment here and I'll draw a quick diagram so we have a bit of a visual of what's going on. Okay, so here we have an object. It starts at a height of 1.8 times 10 to the 7 meters above the center of the Earth. That's the radius. And then we want to lift it up higher to a new location with a new radius. Now note, there's nothing in this question that says this object is in orbit. So basically we have a situation where we've kind of made it hover at this height. It's not moving around like that. And we want it to now go and hover at a new height. So to solve this question, we're going to use the law of conservation of energy, which I'll remind you looks like this. Potential energy initial plus kinetic energy initial plus work done by other stuff. Again, other stuff means things that we don't have a potential energy formula for. And that equals the total energy at the end. Potential final and kinetic final. Okay, so the next thing I like to do with these questions is just go through this formula and think, what things here, what terms do we have and what terms do we not? So in our new formula for potential energy is 0 when we're infinitely far away. That's not the case at any point in this problem. So we definitely have potential energy initial and we definitely have potential energy final. Now, because this object is not orbiting, it's basically just sitting at this location and then sitting at this location, however we manage to do that. There's no kinetic energy either at the beginning or at the end. There'll be a bit of kinetic energy as I move it from here to here, but right at this point and right at this point, there's no kinetic energy. So what that means is I can cancel out kinetic energy initial and kinetic energy final. Those will both be 0. So now how about this work term? Is there work done by things other than gravity? Remember, we don't count gravity in here because we have a potential energy formula that already accounts for the gravitational force. So is there going to be some other force involved in this problem that does some work? I think it's pretty obvious that there should be. I can't get this object to go from down there to up there all by itself. I'm going to have to push on it with a rocket or something like that. So we're definitely going to have some work that's done on the object to lift it up to that new height. Okay, so I think the next step is to then solve for this work. And indeed, that's exactly what the question is asking us for, how much work is done. So let's just rearrange this so I have that work on one side all by itself. I'll leave the work on the left, move everything else to the right. And now I'm going to plug in some formulas. So potential energy, because we're looking at situations where we are pretty far away from the surface of the Earth, and we're moving through a large enough distance that we expect little g is going to change, we can't use our old formula for potential energy. We can't use mgh. We're going to use the new one. I'm not sure why I put that 2 down there. Let's take that away. So I've got two potential energies here and here, and they both have the same formula, and they're being subtracted. Now, although these two formulas, as I've written them, look identical, we should notice that there are some differences. M1 and M2 are going to be the same at the beginning and at the end. But what's changing from the beginning of the problem to the end of the problem is the radius. So this r down here is different from this r here. So I should probably label them differently. Since this r is the r for calculating the final potential energy, I'll call that r final, and the other r will be r initial. Now at this point, we're welcome to just start plugging everything in. We know M1, the mass of the object. We know M2, that's the mass of the Earth. We know big G. We know R final, that's this guy. We know R initial, that's that guy. And then we've got the same things up top over here. So we know everything we need to plug stuff into this question. What I'm going to do, though, is I'm going to do one extra step of algebra first, just to save me a little bit of writing and to save me a little bit of calculator work. Because so much stuff is repeated twice here, right? M1, M2, big G are the same in both of these terms. So rather than writing them down twice and typing them into my calculator twice and then introducing just extra opportunities for me to make an error, I'm going to factor those two things out. Then I'm left with negative, and basically everything from this fraction has been pulled out, so all I've got left is a 1 over r final minus negative 1 over r initial. I don't love all of these negatives here, so just to clean that up a bit, I'm going to remind myself that when I subtract a negative, that's the same as just adding a positive. So I'm going to rewrite that way on the next line. But at this point, I think I can just plug some numbers in. So work equals M1 is 4,500. M2, mass of Earth, 5.97 times 10 to the 24. Big G. (6.67 times 10 to the negative 11). And then I have negative 1 over our final 4.2 times 10 to the 7. I got that guy from up here. And then, as I said before, when I'm subtracting a negative, that's the same as adding a positive. So I'm going to write this as plus 1 over our initial 1.8 times 10 to the 7. And that gives me 5.69 times 10 to the 10. Joules. So a quick recap on what we've done in this problem. We had an object that was hovering somehow, a certain height above Earth. Then we needed to move it to a higher height, so we had to do some work on it. We had to push it up there, again, somehow. And to figure out how much work was done, we used the law of conservation of energy. We said there was basically no kinetic energy either at the beginning or at the end, because there's no requirement that this thing be doing anything other than hovering. It didn't need to be moving. It didn't need to be orbiting. And that showed us that the work that was going to be done to do that was just the difference in the potential energy between the two locations. Remember, potential energy now in these sort of problems has a new formula, a little fancier than our old one, and it has a negative sign in front of it. Okay, so let's look at another problem. "250 kilograms of garbage is dropped from the altitude of the International Space Station. At what speed would it impact Earth if there were no air friction?" So it's kind of a similar type of problem to what we had, only kind of in reverse. In the first problem, we had an object down here, and we were lifting it up. In this problem, we have an object up at a high altitude by the International Space Station, and it's dropped. So I'm going to start with, again, just a quick diagram here. Okay, so I have an object starting up here. It's at an altitude of this. Altitude means the height above the surface of the Earth. So right away we should be thinking, okay, we're going to have to add in the radius of the Earth here if we want to get the distance from the center. And it's dropped, so it falls all the way down, and we want to know its speed right there, just as it impacts the Earth. So initial is up top, final is that dot down at the bottom. Just like the last question, we're going to start with the law of conservation of energy. And again, we're going to see if there are any terms here that can just be 0. So at the very beginning, remember, potential energy is 0 when we're infinitely far apart. That is not the case in either of these situations, so I clearly am going to have potential energy at the beginning and potential energy at the end. Kinetic energy, however, is going to be 0 if something's not moving. And this problem says to assume it starts from rest. So right up here at the beginning, I have no speed, I have no kinetic energy. So kinetic energy initial is going to be 0. At the end, as it hits the ground, again, we're not infinitely far away, so I can't say potential energy is 0. This is a bit different from what you're used to. Sort of up until now, we probably would have said potential energy is 0 at this point because it's on the ground. But the ground is no longer our reference point. Infinity is. So when we are down here, we do have potential energy and we have kinetic energy because we picked up all that speed from falling. And now how about work? Is there work done by things other than gravity, which is the only force we have a potential energy formula for right now? Well, no. To fall from this height down to here, you don't need any force to act on you. This thing is just literally dropped. It is a projectile. It is in free fall. Its free body diagram has only one force acting on it, and that is Fg. So yes, gravity will do some work on it, but that's already accounted for here and here, so we don't count it here as well. Because there are no other forces, note that we are ignoring air friction or air resistance. There can't be any other work done on the object. So this guy is going to be 0 in this situation. So let's solve for our kinetic energy final. And then once we've got that, we can use that to find the speed. So I'm just going to rearrange this for kinetic energy final. Okay, and let's again sub in our new formula for potential energy. And again, if you like to just get into the calculator as soon as you can plug numbers in at this point. We know M1 is 250. We know M2 is the mass of the Earth. Big G we obviously know, and these two R's are going to be different. In this case, the first one is R initial. This guy goes with potential energy initial. The second one is R final. So I should probably label them as such. R initial is going to be the radius, the distance from the center when we're up here. So that's going to be my 3.5 times 10 to the 5 plus the radius of the Earth. And my R final is going to be how far I am from the center of the Earth at the end. And that's going to be just the radius of the Earth. What I'm going to do is I'm going to factor out that M1, M2, big G, because I like to just avoid typing more things into my calculator than I have to. Again, I'm just using this idea we used last question that subtracting a negative number is the same as adding a positive. That just cleans things up a bit. So that's how I got this plus sign from over here. And our final is just the radius of the Earth. And all of that equals kinetic energy final. Just to kind of save a bit of space, I think I'm not going to bother writing down what the numbers are for M1 and M2, or for big G. Big G we all know. M2 is the mass of the Earth, and M1 is 250 right here. So if you plug all of those in, you should find that the kinetic energy final is 8.1147 times 10 to the 8. Now remember, what we're actually looking for is the speed at which it would impact Earth. So we're looking for the speed final, not the kinetic energy final. But we can easily get the speed now that we have the kinetic energy. Because we know that kinetic energy is equal to 1/2 the mass, which is 250, times the speed squared. So if I then take that and solve for V, I'll get 2,550 meters per second if I round to 3 sig figs. All right, so let's do one final example with the law of conservation of energy and our new formula for gravitational potential energy. And I picked this example because it has a scenario that's just a little different from the two we've looked at so far. So, an asteroid falls towards Earth from really, really, really far away. I've used 3 reallys here, so something's probably up. How much energy is released when it impacts with the Earth? So it's kind of a little bit like the last question. We have an object far away from Earth. Gravity pulls it towards Earth, and we want to know the energy it has as it hits Earth. We want to know the kinetic energy, really, that it has as it hits Earth. So a lot like the last question. But there's these 3 reallys here. So what's going on? Well, part of being a good physicist or a good engineer, I often say, is not necessarily knowing exactly how to solve every single problem exactly as it's given to you. But a lot of it is about knowing which assumptions you can make, which things you can ignore, which things are negligible. Being able to get to an answer that's maybe not perfect, but is really good, and being able to get there in a reasonable amount of time. So the hint here, the really, really, really far away part, is sort of guiding you to suggest that if this thing is really far away, maybe we can assume it's infinitely far away. It's impossible to be actually infinitely far away, but it's also impossible on planet Earth to have actually no air resistance. Yet that's an assumption we make all the time. So I think a fair assumption to make here is that really, really far away, it means we can basically treat it as if it's infinitely far away. Just like really, really low air resistance means we can basically assume there's no air resistance. So, quick diagram. We'll write down the conservation of energy formula, and then we'll hop to it. Okay, so we have an asteroid starting up here above Earth, where R is essentially equal to infinity. It's approximately equal to infinity. Earth pulls it down, moves closer and closer, and we're interested in it right as it first strikes the ground there. Basically, on impact, it has a ton of kinetic energy here. And over the course of a split second, the Earth is going to bring this asteroid to a stop. So it's going to get rid of all its kinetic energy. But because kinetic energy is conserved, all that energy has to go somewhere. And that is that's the energy that is released. So as it hits the Earth, all the kinetic energy it has is going to be immediately removed as the Earth brings it to a stop and converted into heat, light, sound, all those good things that are going to kill the dinosaurs or whatever happens to be on Earth at this moment. So basically, we're looking for the kinetic energy at this point. And we know that is what's going to be released when it impacts Earth. Okay, let's see if anything is zero. So, because we start really far away, at R is approximately equal to infinity, that means we do have zero potential energy initial. Potential energy initial is zero because R equals infinity. What else do we have? It doesn't explicitly say it in the problem, but this feels to me like this asteroid is being dropped. It's not thrown towards Earth. It's not fired towards Earth. It's not sent towards Earth. It falls towards Earth. So that gives me the sense that this thing sort of starts with no initial velocity. It's out there in space, just sort of floating, and gradually it gets pulled closer and closer to Earth. So that means I'm going to say its initial kinetic energy is zero. Okay, what forces are acting on this asteroid as it falls towards Earth? Well, there's just one. It's gravity. And yes, gravity does work, but work done by gravity is accounted for here and here already, so I'm not going to put it there and double count it. And that work other term is only for work done by forces that don't have potential energy formulas. And there's none of those in this equation. So this ends up looking a little bit weird. We have nothing on the left and potential and kinetic energy on the right. So 0 equals potential energy final. Plus kinetic energy final. And kinetic energy final is the thing we're looking for. So to isolate kinetic energy final, I'm just going to move this potential energy guy to the other side. It's nice because it'll get rid of that negative sign too. And then we can plug some stuff in. M1, massive asteroid. M2, massive Earth. Our final, so that's just going to be that distance there, or the radius of the Earth. And if I plug that into my calculator, I get something completely wrong because I've neglected to put big G in my calculation. So let's fix that and add that in right now. That should fix things and give me a final answer of 1.47 times 10 to the 24 joules. Now, remember, that is the kinetic energy I have as I hit the ground. What I'm actually being asked for is the energy released when I impact the ground. And those two are going to be the same. As I hit the ground, there's like a split second where I come to a stop. During that split second, my height isn't really changing at all. So the potential energy doesn't change. But my kinetic energy goes to zero. The Earth is going to stop the asteroid in a split second, and all that kinetic energy the asteroid had needs to go somewhere else, and it's going to be released as heat, as sound, as light, etc. So hopefully those examples help to give you a sense of how to use the law of conservation of energy with this new formula for gravitational potential energy. Some key takeaways here. Being able to identify situations where kinetic energy is zero, like we did in the first problem. Situations where work is going to be zero, like we did in the second problem and in the third problem. And situations where potential energy is zero. And that is this new thing that's going to happen when R is infinity or close to it. Other takeaways from this lesson. There's a lot of big numbers to plug into formulas here, and you're going to run out of space on your page pretty quickly, like I did a few times. So a trick you can use, if you would like, is when you've got a couple of potential energy terms like this, feel free to factor out some stuff. Often you can factor out M1, M2, big G. You don't have to. I've said this kind of a few times. If we wanted to just start at this line here and plug numbers in directly, we absolutely could. We just need a lot of room on our page.